This week's lecture is on the global positioning system. So most states have some kind of minimum technical standards. Maine's no different. Most of their regulations center on boundary. That's the typical project that a land surveyor performs that the public gets involved in, and so that's why boards of registration are created to protect the health and welfare of the public. Other states have more general standards, but Maine's kind of centers on boundary determination. But again, they have other sections, and one is equipment. So the licensee shall maintain, check, calibrate equipment to ensure the equipment is giving results compatible with its intended use and achieving the precision that is required or reasonably expected by the client. So that's just telling you that you have to maintain your equipment, perform some kind of a calibration. There's no GPS calibration baselines, but you can certainly just take it to a point of known coordinates and elevation and do an opus solution to see if your equipment is calibrated properly, or that if the other aspects of the survey system that you're using, that would be the data collector and the associated files, like a geoid file or a control file or state plane projection files, datums, all of that coupled together is giving you results that you can expect. And that way there you're reasonably sure that you're going to be giving the client what it is that they're asking you to do. And again, it's your call as to equipment, procedures, and methods, and you have to make sure that you're giving the client what they need, the precision that is required or expected by the client. Those are two different things sometimes. The typical thing is, just give me a rough idea where my property line is. Well, that's a trap. Never do that. But sometimes, they'll only ask you for some rough grading or something along those lines, and it inevitably turns into what they use to set a pipe or grade a field. And again, that's another trap that you really shouldn't fall into. Either do the work to what's required, or don't do it at all. But that's your call when you become licensed. It's a business, and those are business decisions. Mass handles it the same way. Measurements are the intended purpose of a work product, which is the deliverable, whether it's staking out a property or a building or existing conditions plan, shall dictate the accuracy and precision of the field measurements, the measuring equipment used, and the manner of its use. So you have to decide all of those things to meet the client's needs, because you're the professional. They don't know what they need. They might tell you what you should be doing, but you shouldn't really be allowing that to guide you in your work. So And these things apply to total station leveling, GPS, LiDAR, whatever it is you're performing for the client. So the global positioning system, it was developed by the Department of Defense for mostly navigation, positioning, and targeting. And it's a 24-hour day, all weather, anywhere in the world system. It is a system that allows the military to do all sorts of missions. Now, we don't have access to the same frequencies that the military has. They can pretty much get to plus or minus a foot, whereas we might be 100 feet using the same methods and equipment. We have to do some processing of the data to get down to the centimeter. So there's a space segment, which is the satellites, and they orbit the Earth at 20,200 kilometers, and they're inclined 55 degrees, and they have this 11-hour, 58-minute period. And the reason they did that was that if that makes them not be geosynchronous, which means you see an ever-changing constellation of satellites going over your head, and the satellites are the control for your survey on a GPS project. So if you just had geosynchronous satellites up there and one of them went amiss, you might not know it right away. Whereas the way they're inclined, the satellite constellation that you see is constantly changing. It's coming up on from the horizon and transiting across and down the horizon. Over the course of a day, you'll see any number of satellites. And it's intentionally created that way because they want the control to be changing. That creates redundancy. That creates that warm feeling that you've got a lot of measurements to a lot of different control points, which are the satellites, and that gives you a good result. And it's going to pop out any bad data. The control segments, those are just tracking stations. They track this. When you use RTK, you're getting what's called the broadcast ephemeris. It's a estimation of where the satellite should be at that time when you observe it, and that's what these control stations do. They monitor where the satellites are, and they collect information, and then they compute the ephemeris, which is the satellite's orbital positions. Now, the broadcast, which is what the satellites include in their message, is an estimation of where it should be. So if you're using RTK, you're at the mercy of that broadcast satellite ephemeris, and RTK is an instantaneous observation of the GPS satellite. So if there's any error, any clock error, any kind of errors in there, multipath, or it's going to be in your solution. So you have to find a way to mitigate that problem, and you can either do it through redundancy or not using RTK for some purposes. The control segment tracks the satellites, and it does create other ephemerises, and they come out. It's certain times there's a rapid, ultra rapid, and then 21 days or so later comes the precise ephemeris. And if I was doing any kind of control work with elevations, I'd probably wait for the precise ephemeris, because if you're doing static, I mean, you may as well just wait for it. The user segment is the GPS receiver, and there's any number of uses for GPS receivers. I have, you have one in your phone, in your truck, handheld Garmin's, my survey grade receiver. So there's any number of quality of solution receivers out there, and again, you pick the right tool for the job. A trucking company doesn't really care if it's 300 feet. They just want to know that their truck's on the interstate and it's heading west, and it should be here and this time, and they can pretty much tell that. Whereas if you're doing control work, you want to get the centimeter accuracy, and you're going to do that with methods that will return that kind of measurements. So the space segment, like I said, those are satellites. So each satellite circles the Earth twice a day, and they're in slots, and these are set up so that you can see 4 satellites in virtually any point on the planet, and that's because these were the requirements for the DoD. And again, they use different signals than we can't see the military signals. We see the civilian signals. So whatever they see, they just need to see 4 satellites, and that serves their purpose. If you drop a bomb here or 100 feet away, I don't think it's really going to matter. But they do use GPS to guide weapons and navigate and surveil. So again, this was set up by the DoD for their purposes. So this meets their purpose. We've taken it and we've created methods and procedures to adapt it to our needs and our precisions and accuracies. Control segment, again, master controls in Colorado. Then they have all these monitoring sites around the world that so they can see all the satellites at any given time. Yeah, this is the control segment. So the user grade, we use survey grade GPS receivers, and we use 4 centimeter accuracy. We use dual frequency receivers. There are single frequency. I owned single frequency in the beginning, back in 93, 94. I had some Trimble single frequencies, and they're fine. They just don't. They limit the length of a line that you can measure, and you have to do a little more work processing it. You have to pick some models to accommodate that you don't have dual frequency, because dual frequency allows the solution to remove some of the errors by differencing, and we'll see differencing in a little bit. Let's see. So dual frequency also allows you to use, on the fly, RTK, kinematic, those kinds of survey methods. The signals we can see today are L1, the coarse acquisition signal, L1, L2, those are the dual frequencies that we saw for a long time. L2C and L5 are newer frequencies that we hadn't always seen. They're new to the, I say new, past 10 years. But what these signals do is they carry information, and these signals are developed by the DoD because it's their satellites, and they put what information they want on them. But the additional frequency signals get you more information. You can also purchase what they call correction services for like precision agriculture, machine control, things like that. Positioning, survey positioning. I think Trimble has a correction service. John Deere has one. I think maybe Caterpillar has one. And what they are, their own satellites are up there, geosynchronous over the United States, and they calculate where you are based on the location of your receiver, and they make the corrections that take out that 30 feet of question, and it brings you down to the centimeter level. I was watching a precision agriculture video, and according to them, they can drive down a field and plant, and then when they need to fertilize, they can drive down the field in the same exact position and drop the fertilizer right on the line of planting. They don't have to spray anymore. They don't have to overspray. None of that. That's pretty good if it's true. That was my cat. Sorry about that. So the structure of the GPS signal, it's one-way ranging, okay? And the receiver you have sends out no signal, okay? It does, just moving my keyboard here. And that's a military requirement so that they remain concealed while getting the GPS signal. And each receiver has a unique set of codes known as the gold codes that identify the origin of the signal received, so you know what, because the satellites are sending out the same signal, they need some way to identify themselves. So ranging is when they compare synchronous signals from a receiver, and that's how the GPS receiver can determine its distance. It's kind of like they do like a trilateration where they just have distances between receiver and satellites, and by getting multiple distances from multiple satellites, they determine where they are, and they do this through the ranging. And so each GPS satellite broadcasts data to support position determination. So the data includes, the satellite time of transmission, the satellite's position, the satellite health, the clock corrections, propagation delay effects. That could be atmospheric problems, time transfer to a UTC, universal time coordination, and constellation status, because some satellites might be out, some might be out of service, and they may be moving a spare into a position or something like that while you're working. One thing you have to know about GPS is the timing. The clock is everything. You have to be able to know what time it is so that you can solve your ranging. So the integer ambiguity is the problem that has to be solved to relate the signal to distance. Okay, because the GPS receiver only can determine that this final partial wavelength, but it doesn't know the number of full wavelengths that have passed during the transit time from when the signal left the receiver until it arrived at, when the signal left the satellite to when it arrived at the receiver. Okay, so by knowing the wavelength and the time, and like I say, clock is everything with GPS. It doesn't matter what you're doing. If the clock's not working, then you're not getting position. So you know the time it left and the time it arrived. So now you know the travel time, and we know the signal velocity, we know the partial wavelength that we looked at, and from that we can solve the integer ambiguity, which is the number of full wavelengths, and then we add the partial, and then we can calculate the distance. And that's a quick and dirty example of ranging from a satellite to a receiver, and that gives you your distance. And it's going to do this from it's going to do this from every receiver it can see based on the criteria that you've set, and mostly the criteria has to do with masking. At some point you have to decide what mask you're going to put on this, and it might be 10 degrees, it might be 20 degrees, because as satellites come up through the horizon, it goes through more atmosphere than it will when it gets up here and it gets up high in the sky. The signal goes through more atmosphere. I shouldn't say the satellite. The satellite's out in space 20,000 kilometers, but the signal will go through more atmosphere, so the atmosphere is thicker, may have rainstorms, it may have a lot of issues going on. But when it gets up higher in the sky, it's going through less atmosphere, and you get a cleaner signal. There's a thing called signal-to-noise ratio that you can look at to see what kind of a mess the signal is. But so you're going to set a mask, and you're going to say, I don't want to see anything below 15 degrees is a pretty typical one. Some people set it to 0, and just you can mask it out later in processing if you're doing post-processing. You can't do that kind of things with Opus. If you're doing an Opus solution, Opus is a wonderful, wonderful thing, but it really requires very clean data. So a lot of times people will, let's see, get my pen back here. Oops. So you might have set your mask at 0 and run it through Opus, and it doesn't give you a solution. But you can go in and edit it's a text file. Rhinox is the file that you used to send. But if you convert it to Rhinox, you can go through and look at what's going on. And sometimes I find that if I need 30 minutes for an Opus solution on this satellite, I'll run it for at least 40. And I just erased the first 5 minutes at the end and at the beginning. And sometimes that's enough to clean it up for it to go through Opus. Sometimes not. Depends if you're using static or rapid static. They're two different processing engines. You can run it through both and see what happens. But if you're going to process data, you post-process data. So what's going to happen is you're going to start doing some differencing. You'll be seeing. Of course, we're doing relative positioning, so we need 2 satellites. That's the only way to do differencing, because if you had just one satellite, receiver, 2 receivers, because if you just had one satellite and one receiver, you wouldn't. There'd be nothing to difference, because you just have one ranging solution. So we have to have a minimum of 2 receivers to do post-process static. Single differencing, it subtracts at 2 simultaneous observations, and that's what differencing is. It's going to subtract simultaneous observation. So single differencing eliminates the clock bias and ionospheric and tropospheric refraction. And don't ask me how it's done. If you want, Alfred Light wrote a book on GPS satellite surveying. You should read that. They'll tell you everything you want to know. So double differencing is the difference from 2 single differences obtained from 2 satellites, and that eliminates the receiver clock bias. And then triple differencing is 2 double differences from 2 epochs, and what that means is 2 satellites have been observed, and you at one instance, and then maybe 2 minutes later is the second epoch, and it's the same 2 satellites are observed by the same receivers. Otherwise you can't difference. Satellites in 2 epochs that aren't the same receivers. Satellites, excuse me. So this removes the integer ambiguity, which is the key to solving post-process static GPS. So the geometric range results, and that's the distance. And it's the first estimate of the receiver's position. And it's the first estimate because even though we've differenced these triple, double, and single differencing, we still have to go through a least squares adjustment to determine the final position of the receivers. So here's some typical requirements for GPS surveys. Static survey, 1.5 centimeters. Vertical is 4 centimeters. Rapid survey, rapid static, 3 centimeters, 8 vertical, kinematic, which is moving, 4 centimeters, 6 vertical. Hydrographic surveying, it's not horizontally, it's 3 meters, but it's decimeter and a half vertical. There's a little more uncertainty in hydrographic surveying due to organic layers on the bottom and things like that. They have to deal with, just like the satellite signal going through the atmosphere, they have to deal with the hydrographic signal going through from the echo sounder, going through different strata of water, whether it's colder or denser, salinity, things like that. So topographic is 1 to 10 millimeters. That's, good luck with that. Cadastral, 1 to 10 centimeters. It depends on, the need. I've heard the chairman of the board of the Mass Board of Registration say that boundary surveying has to be to the 100th, period. So, good luck doing that with GPS. And ground control points, 1 meter. Ground control points should be done static. So I don't know what control you would use at 1 meter, but that was from the 2021 Federal Radio Navigation Plan, which is the civilian. There's a civilian group that oversees the civilian side of the GPS system. So when we do a static survey, we've got a known position that we're somehow going to locate an unknown position from. And we do that through the single, double, triple differencing. And then we do an adjustment of some kind, either through a software package like Trimble Business, like a Geomatics, StarNet. There's 100 of them out there. Geolabs is another one. But we have to see the same satellites. Okay, you can see we're going there and there, there. So whenever we want to position something, we have to be able to see the same satellites from different receivers. It does us no good if only this receiver saw these satellites and this receiver saw those two satellites. We won't get a solution. Okay, we have to see the same satellites from the same receivers, or we can't do our adjustment to find out our solution. As a typical, I did 100 of these back late 90s, early 2000s. I haven't done one in probably 10 years. It's a lot of work, and unless there's a need for it, the control ends up getting. I did a bunch of GPS networks in towns that, over the years, they just got knocked out. So most control that I just used Opus for years, and you just put that in your survey report. That you show the plus or minus in your report, and people know what it is you're talking about. Like I say, this is like they used to call them campaigns because it was a big deal. You had to set all these points, and you had to have observation to the sky, and then you had to be able to see the same satellites at the same time. It was quite a lot of work, and they're still out there. I've got there's a primary network I set way back in the let's see, late 90s, that when we got dual frequency. That's still there. But we spent a lot of time finding the right points and setting the points such that they would not be disturbed. And still a couple of them did. So it's like you say, if you go in and you look at data sheets and recoveries and things, a lot of the stuff it's bulldozed by a lot of the control in the early days was set alongside interstates or state highways, because that's who was doing the control. They were doing it for these highways, and then as the highways widened, all these control points just disappeared. So a lot of work, and to have it disappear wasn't really economical. So like I say, a lot of the control now is just Opus. It depends what you want. I can do a 15-minute Opus. I can do an hour. It's all going to depend on what it is you need to deliver to the client. But anyways, so this is a big static network. Where's my pen? This is a big static network, and like I say, it's a lot of work. So just so you know how it's done. So this is the same 1 and 2 from the previous slide. So the first occupation session would be stations A, B, C. A, B, and C. So AB is called a trivial baseline, and AC and AB are non-trivial, and that has to do with statistics. And you've used the information that's A received, and you solved AC, and you used this B. That's all about. To solve BC. So now these statistics are already in the adjustment. So that's why they call this non-trivial. They don't use this baseline really doesn't get used in this adjustment. You'd have to occupy it again to capture data for that line, because you've already used it to solve this line and this line, so you can't use it to solve that line. So that's the difference. From 3 receivers, you get n-1 baselines. So 3 minus 1 is 2. So for every 3 receivers, you're only going to get 2 baselines to adjust, to put into your adjustment. And now you come over to 2, session 2 here, and we're going to do ACD. So we got A, C, and D. And again, n-2, we're only going to get 2 non-trivial baselines and 1 trivial right here. But the other thing to consider is now we've captured AC twice. So we've now got a redundant observation. And that's the goal of these networks, is to capture the data, get non-trivial baselines, and get redundancy. So you might have to you just don't occupy this once. You might have to occupy this twice, and maybe you occupy this and go over here, and then you use this and make that the non-trivial baseline, and you get a redundant observation here because you've got it from this loop and this loop, and now you've got a cross tie, and you've got a third redundant observation. It requires some thought. So now you've got all of these measurements between all of these points, and don't forget, so this is your control, your known. You've got to get this somehow into your network with a non-trivial baseline. So, you can't connect these unless you have a non-trivial baseline. So you're going to occupy these things over and over again to have redundancy and get non-trivial baselines. And the redundancy is sometimes required by the criteria. So loop 1, 3 receivers in a simultaneous observation, 3 baselines observed, 2 non-trivial, 1 trivial. The measurement observations are used to compute AC and BC, and no additional measurements exist to compute AB. So you're only going to get 2 baselines out of that. Now, when you start to do your static adjustment, the first thing a lot of programs have you do is loop checks. And it's going to say, okay, here's 1. These 3 stations are connected through observation. And it's going to run a loop check. It's going to say, okay, distance to here, distance to here, distance to here. And if you don't have non-trivial baselines, it's not going to give you a loop solution. So once you have non-trivial baselines all around, you can do a loop check, and it will tell you the error that exists in this observation. And then after you've checked all your loops and they all close very well, then you do what's called a free adjustment, where you hold one control point, and then you just adjust everything. And all that is to see how your control fits as it propagates through all of your observations. And it will tell you if you have nice homogeneous observations. And if it doesn't propagate through very well, then you got a bust somewhere and you have to go find it. But you really should have seen that in your loop checks. And then finally, you're going to do a constrained adjustment where you start holding multiple control points fixed at the same time. And the static adjustments can require a percentage of known horizontal and a percentage of known vertical based on how many points you might be gathering coordinates on, looking for solutions to. They don't want you to push one coordinate through 100 points because there's really no check on anything. It's just like not running double loop on your levels. So you need to have control that's well spaced throughout your project to find coordinates on unknowns. You need to have a percentage of redundant baselines. They're going to want to see 80% redundancy in your baselines. Whether it's 1, 2, 3, 4, it's all redundant measurements. You're going to have loop closure plus or minus criteria. They're going to have to close within so many millimeters, centimeters. And then at the end, when you finally do your constraint adjustment with all your control, horizontal and vertical included, there'll be some kind of statistical test criteria. The most general one is chi-square. And it's going to have a value based on the degrees of freedom, and that's what is the number of knowns subtracted from the number of unknowns. So you want to have a real high degrees of freedom, which is redundancy, and that's going to set the criteria, your upper and lower passing criteria on your chi-square test. Again, that's a real general look at static surveying. There's a GPS class Ray teaches that I'm sure you'd be thrilled to take. So when you start looking at solutions in your adjustments, there's autonomous. It's just like a Garmin or your cell phone. There's float, and that just means that all the systematic errors haven't been resolved. It says 1 to 5 meters. It could be 100. You don't know because it hasn't solved all the errors. And those 1 and 2, autonomous and float, aren't really solutions I would ever use for anything because you don't know. I mean, 1 to 5 meters, could be 25 meters or 50. You can't tell the client. You don't know. And fixed ambiguity is all systematic errors are resolved so that the solution nears centimeter accuracy. This is all I'd ever use for positioning, unless I'm driving a truck or something, and you don't care. You're not looking for centimeter positioning. But you're the professional. I'd never use it in my work, except for a fixed ambiguity. And again, that's what RTK comes down to sometimes, is all the inherent errors are there, and unless you come back and you check it, you're really skating on thin ice because you have no way of knowing whether there was a hiccup, cycle slips, there was any number of things. So these are some of the errors you can have. Precise or broadcast orbit error. So if you're using RTK and you've got the broadcast ephemeris, then you're subject to whatever errors are in the estimation of where that satellite is. Satellite clock errors, like I say, everything is timing. You need to know when it left the satellite, when it got to the receiver, those kind of things. The clocks in these satellites are some kind of, I don't understand how they work, but they're some kind of an elemental clock, like rubidium or cesium, and that's what keeps time in these satellites. You could have ionospheric effects. Again, you're going through the atmosphere, like the troposphere. You could have also, it could be raining, it could be barometer could be dropping, could be rising. And don't forget, if you're using 2 receivers, they could, you can use 2 receivers to measure from Boston to San Francisco. That's a legit use for those receivers. But the weather conditions might be completely different in both places. And that was the one thing with single frequency. They limited you to 5,000 meters because that allowed you to be sure that the atmospheric conditions were probably the same. I mean, 5,000 meters is, 15,000 feet, and that's about 3 miles. So, unless there's a storm rolling through, I lived in the Midwest. Yeah, you could see a storm, coming down one of the highways sometimes because the highways ran east-west, even the county roads, and you could stand there and see it coming, and at some point a sheer wall of rain would transit over you. So typically you have to be aware of that dual frequency lets you measure long lines, but the atmosphere may not be the same at both ends. So you can only choose one model. I think the typical one is Hopfield, I think, and but that differencing helps eliminate some of these effects. Multipath is when the satellite signal comes down, it should go from the satellite directly to the receiver. But let's say it bounces off the mirror glass on a building and then hits the receiver. So now it's transited a longer distance than it should have. So now when it calculates the time left, the time received, it's just not going to be the correct ranging. So multipath is a real problem, more of a problem than it was. A lot of receivers, have construction that allows them to mitigate some of that in the software that looks for that to eliminate it. But in the old days, they used to use what they called a choke ring antenna, and it was just a bunch of circular baffles around the receiver that would catch anything that didn't directly hit the antenna reference point, where the antenna was. And newer. That's what ground planes did. They kept the signal from hitting the ground and bouncing up and hitting into the receiver, because they were big sheets of metal that you put the receiver on. Probably nobody knows what I'm talking about, but so ground planes used to do that mechanically, whereas now we can do it with software and better construction of these smaller receivers. Height of phase center above mark. Again, when a company comes out with a receiver, they send it out to the Gnss Corbin facility, and they have a test line out there. They used to set them on these pillars, and they would just run them for days just to get an immense amount of data, and then just parse through the data to see. And what they were doing was they were determining the offset from where the signal hits to the actual location of the phase center of the antenna. And if you look at some receivers, they'll have it on it. There's an antenna reference point on the bottom for the pole to measure 166 millimeters to the phase center of the antenna for height. And Gnss creates a offset from the antenna to the phase center. It's an X and Y, and they publish these, and you just put them, you input them into your software as a file, and the software makes the correction from where the antenna should be to where antenna phase center is. And now they have this robot arm mechanism that tilts it and turns it and all these kind of positions, and all along capturing the data for the signal. So they're actually getting a better idea of what the errors are, and instead of it just being stationary and horizontal. So there's a bunch of coordinate systems in GPS. So there's a celestial coordinate system for the position of the celestial objects, the satellites. Sometimes they're called SVs, space vehicles. So then there's the geocentric coordinate system, X, Y, and Z, which is what the software or the receiver handheld, the data collector might be showing you. They'll show you X, Y, Z. Or you can have geodetic coordinates, latitude, longitude, and height. But that's not an elevation. And then we transform geodetic coordinates into north and east and elevation, state plane, projection datum units. We can calculate between all of these. We can go from state plane to geodetic, geocentric. They're related to each other mathematically. They have to be. But latitude, longitude is usable for us. You could navigate by that on a airplane or boat. And then positioning, we use geodetic coordinates, state plane, northeast. So now this height is something we'll look at a little later, because it's not elevation on the ground. So there's corrections, like I said. So if you've got a set of receivers, one might be called a base, one might be called a rover, and you're going to set the base on a known point, or you're going to acquire position on the base before you begin your survey. And then you're going to start moving around with your rover. The rover is going to have a estimated position, and the base will send the correction over to the rover, and it will correct its XYZ for a true XYZ. And then of course you can display anything you want in your data collector. You can northeast, ground, whatever. So there's another virtual reference station. It's a little different than base rover. It creates a virtual base station next to the receiver. It's one company's solution versus another company's solution. 6 in 1. Whatever you're comfortable with, whatever works for you. It's a little different methods, but like I say, whatever works for you. You can see here, that's the DOT or whoever, Trimble, whoever. And there's your rover, and then there's your VRS base station. It's a I guess you could say it's in the cloud somehow. It's virtual. It's not. It doesn't exist. Not like a second receiver would exist physically on the site. This is a virtual base station. So when we start to collect detail with GPS, we just have to set it up, and so here's and these aren't correct anymore because Maine just changed their they just started broadcasting multi-constellation finally. I shouldn't say finally. It worked for them. They're the user. They're paying for it. So, it's not my place to say anything. So, you just, the protocol, the correction, what is it? Network RTK. Okay. And then whatever manufacturer you have, and then the receiver, you put it in, and this is that elevation mask I spoke of earlier. 13 degrees, you can set it to 20. So you have to read your receiver's manual to understand what height you're putting in. Is this the height of the pole? Is this the height of the pole plus the offset from the antenna reference to the antenna phase center? And then again, you just set it up. We're collecting in the controller because that's where the SD card is, or that's where the file's created so that you can transfer it to the computer. And you need an IP address. And you need some kind of logon and password. Mains is free. You just email them and they'll give you a username and a password for your receiver and you can connect. And then this is going to ask you some questions. Again, you know, when you're doing a topo survey, precise or quick, you want fixed solutions because, you know, you use anything else and you never know what you're going to be getting. It could be 5 meters, could be 100. Again, auto topo, fixed only. And then these are some, you know, when you start setting stakes, they're going to, you know, tolerances 5 centimeters. It's a lot. 5 centimeters. You know, I've only done rough grading. I shouldn't say rough grading. I've really done grading that was of such importance that it could be 3/10 to 5/10 out and it made no difference. That was the tolerance on the grading. You know, that's not grading for a parking lot. That's not grading for a sewer line or anything like that. This was just a field that they put up a structure and they were just cutting in to the existing grade. And they said, you know, they give you the tolerances. We'll look at that in 202. But, you know, the contract has to have the tolerances. You don't make these up. The client has to tell you what they are, because staking out grading that's plus or minus 3 to 5/10 is a lot less intensive work-wise than staking out grading of 2 to 5/100. It costs a lot more money, so the client has to be, you know, the one that delivers those things, or he tells you what he's doing and you say, well, then I have to do this and this is how much it costs. And then we just got some point numbers and different parameters and GLONASS, things like that. And you have to determine what you want to use to set that up. And then detail is just like anything else. Once your parameters are set, you're connected to the VRS, the RTK network, whatever it is, the correction system that you're getting. And then you're going to go walk around and the routine is the same on most data collectors, whether you're connected to a total station or a GPS receiver. Same difference. It's going to give you cut, fill, come, go, right, left, and yeah, some kind of way to get you to where you need to be. So one thing that I just want to explain is grid to ground. So when we saw that latitude, longitude, height, that was a grid height. That wasn't, okay, that wasn't the height, the elevation that we put on stakes. Okay, so, oops. I hate animation. I can't get rid of it though. So this is an explanation of heighting. GOE. I'll have to fix that. So, you know, the green is the terrain. The ellipsoid is definition of the parameters of your projection. You have a geoid undulation, and then you have a mean sea level. And those are the four references that you're going to connect to the terrain that you're on. Now, how do you, just a real quick one, positive is up, negative is down, and there's negative in most of CONUS. That's the contiguous United States, it may be negative near the coastlines. Sometimes you can see here sea level goes up above, or sometimes the geoid will go, depends where you are. Because of geoid undulation, the geoid may be above the ellipsoid. So the geoid can undulate above the ellipsoid, means sea level can undulate above and below the geoid. So you have to be careful and look at where you are. Oops. Oh, here's the equation. So this is the equation that, the height above the geoid, which is your orthometric height, which is what we're going to use in surveying on the ground. We want orthometric height for the most part. If you're doing a control, or you're doing stakeout, something like that, we're going to use orthometric height. But we're going to get ellipsoid height from GPS. And we're going to have a geoid model that's going to tell us our geoid height. Okay, so there is the equation. So our orthometric height is going to be our ellipsoid height minus our height below the geoid. That's the equation right there. So when you look at a control sheet, you go to Gnss data sheets and you want to see control sheet. This is what you're going to typically, you're going to see a lot of information, but this is what you should look at. So there's our H, our ellipsoid height, it's 9.9 meters. There's our NAVD 88 orthometric height, 38 meters, and it's truncated like that because of how it was determined. And there's our geoid height, okay, height below the geoid, and from that we're going to calculate. So 38 equals 9.913 minus 28.023. You have to hold the sign, the SIGN, of the value of n. The equations are set up to just use the values as published. Remember that when you get to 202. So there's our solution 37.936, but they're rounding it to 38 because of how it was determined through orthometric height, was determined by GPS observation and a high resolution geoid model. Okay, and up there is your 83 positions, and so now vertical datums. We had there's been a lot of datums. So 1912, National Geodetic Vertical Datum 29, which was called the sea level datum, but they renamed it NGVD 29 because they figured out that sea level elevation in Norfolk, Virginia was not sea level elevation in San Francisco. There's quite a difference. So and that was because it was 1929. They have geoid models to speak of. We weren't doing a lot of gravity observations, and that's how they determine the geoid model. They do gravity, and a lot of that's done satellite now through GPS. So 29, the sea level datum was 29, was renamed. NAVD 88 is a horizontal. I'll have to change that. Oh no, I'm sorry. No, that's correct. So North American Vertical Datum of 80. I was thinking 83. I'm sorry. So this is correct. So the variable date number 88, established in 91, and it leveled across the country, and it included title benchmarks, but they aren't reflected in there because of the fact that mean sea level is not the same equipotential surface at all title benchmarks. It just held that one at Farther Point, Rumenesky, Quebec, Canada, and pushed that across the country. So we also have distances. We have ground distance, which is normal to gravity between 2 points, which is what we work on. We have geodetic distance along the ellipsoid, which is what GPS is going to give us if we use geodetic coordinates. And then we have a grid along the mapping projection surface. Anything projected is always distorted, and if you get to some other classes, you'll see projections. They can only one thing can be. It can be like an azimuth that's held. Like pilots have azimuthal projections because they need to know the azimuth between New York and San Francisco. So that projection holds the azimuth as true, and everything else distorts. Some things they create these for specific purposes, and that purpose is undistorted and everything else is distorted. If you look at a map, you look at Alaska, and it's incredibly distorted as far as its area because of where it is on the map, on the curved surface of the globe. So that's what they're talking about as far as projections. Some can be, areas can be held fixed, azimuths can be held fixed, but everything else is distorted because it just has to be. So grid scale is the multiplier to change geodetic distances based on the Earth model to a grid plane. Elevation factor, or ellipsoid reduction factor, is a multiplier to change horizontal ground distances to geodetic or ellipsoid distances. And the grid elevation or combined factor is the grid scale factor times the elevation factor. So this factor changes ground distances to grid distance or vice versa. And so when you do your adjustment or opus, whatever it is you do, you're going to get some kind of a combined scale factor, and you're going to go, when you get these coordinates, you need to go to some kind of ground coordinates because you've got grid coordinates. Stay plane, and if you measure between them, you're not going to get the inverse of the coordinates by measuring between them with an instrument because of this distortion. So to get to the ground coordinates, we use what's called the average combined scale factor, this one here. And what that does, it creates its own little mini datum of these points, because you can't use these individually to get to here. You need to create that little datum on your project, and you do that through the average combined scale factor. And so to go from grid to ground, you divide by the average combined scale factor to get your ground coordinates. You'll have to look and see how your controller handles elevation. And then you have to decide what unit you're using, whether it's US feet, international feet. And I know international feet has just been blessed by the popes of geodesy, the NGS, but that doesn't mean it's valid for all these states, because I don't know any state that's changed their legislation to allow you to use it. And I know this is just 110, so you might not be familiar with some of that stuff, but you know, the state legislature and the boards of registration determine what unit of feet each state is. So I'm still using Mass where I'm registered. It's still U.S. survey feet because Chapter 97 dictates it. It gives you the conversion from state plane to from meters to U.S. feet. It's right here, okay? Because you're going to get meters out of GPS typically, and then you're going to go to U.S. feet and ground. Just something to be aware of. I don't know how this continues, but all NGS elevations were done using U.S. feet conversion. And that's just a, if you go to this frequently asked questions, that link right there, number 2, that's where you can read that from NGS. So they publish elevations in meters and feet to the 100th of a foot. And they use U.S. survey foot conversion. So all your elevations from NGS are U.S. survey feet. Sometimes you want to modify the coordinates on your drawing. Sorry about that. So those conversions right here, they look a lot like state plane. So you want to modify them sometimes so they don't look like state plane, so there's no confusion. Even though your notes say one thing, people assume another a lot of times. Well, my students do anyways. They make a lot of assumptions. So you're going to do a shift. Okay, there's no rotation here, so it doesn't change orientation. You're just shifting it north and east a certain amount, plus or minus. And it's shown as plus because of the shift. And I'll pull my notes and add that to this. But the shift is, we subtract that number from the state plane to get these local looking numbers that don't resemble state plane coordinates at all. Just so there's no confusion. I mean, you don't have to do it if if you've converted them from grid to ground and you've noted that they're ground coordinates, then everybody's at their peril if they don't read your notes. But sometimes it's a good practice just to convert these through some modification. And so this is a comparison. This is a job I did. You have to, this is the precision of these distances. You can see, here's a short distance. It's only 1 in 7,700. Here's 1,400, it's 66,000, 149, again, a 500-foot distance. So you can kind of see the shorter the distance, the worse the precision might be. Not always. Here's a 1,000-foot distance. It's only 1 in 18. I think 2 had a problem here. You can see 2, 2, and 2. 2 didn't seem to be working out well. Sometimes that happens. Maybe there was a bad observation when you did 2. Okay, so sometimes you have to look at your results, see if they make sense. You moved them from grid to ground, and you want to check the precision. This was my traverse distance, and this was my opus reduced to ground, and I want to check the difference in the precision. So that's kind of a good lesson to learn. And I think that's it.